can't be there in person today. It was just made impossible because of the train strikes. But hopefully this technology will work. So nice to meet you all this morning. I'm Professor of Intelligent Systems, which effectively means working in artificial intelligence and its practical applications. And I'm at the University of Portsmouth in the south of England. So what I'd like to cover today is I've entitled the talk "The Developments in AI," and I'll start by just saying what AI is. But what I'll do is run through the history of AI from the past to current developments. And I think this is quite important because to actually understand how current AI technology works, you really need to understand where we've come from. And I'll make a conclusion, which is that along the lines of using the right AI tools for the task at hand. I will say that my slides are available. I've already uploaded them to my website at adrianhopgood.com. So you'll find them there, and I put the link at the bottom here. So it's adrianhopgood.com/presentations to get my slides. So first of all, let's start with what is AI. Well, a standard definition is along the lines of mimicking human and you see variations of that definition, but that's a sort of standard definition. But it's a bit vague, and it raises all sorts of questions. Does the AI need to work like a human, or are you just interested in the results? Is the aim to match or exceed a human? Because certainly in certain domains, you can expect AI to certainly be faster than a human. Does it need to be able to explain itself? That's a really hot topic at the moment. Is animal intelligence relevant? And indeed, is all biologically inspired computing a form of AI? So there's lots of questions around that sort of rather loose definition. The other thing is that what we understand by AI is constantly changing. Here's a quote from Rodney Brooks, one of the AI pioneers, who says, every time we figure out a piece of it, let's say a piece of AI, it stops being magical and we say, oh, that's just a computation. So we're currently constantly moving on in our expectations of AI. And to give you some examples, when I first started working in AI in the 1980s, smart automated chess was a challenge which was effectively solved in 1997 when Deep Blue beat a human grandmaster. Character recognition, and I'll talk a little bit about that example shortly. Speech recognition, those were all considered AI challenges, whereas now we think of those as routine. Even though they really are using AI in practice, we're always thinking about the next development. So if we look back at where AI started, I would suggest to you that the starting point was 1950 with the publication of this paper by Alan Turing, Computing, Machinery and Intelligence. And he opens his paper with the question, I propose to consider the question, can machines think? So really setting the start of AI, and he proposed the imitation game, which we now usually call the Turing test, where the argument was that if you can hold a conversation with a computer system and not be able to distinguish it from a human, then it's passed the Turing test. Then in 1955, we had the first published use of the phrase artificial intelligence. It was a proposal for what they called the Dartmouth Summer Research Project on Artificial Intelligence. That event, generally known as the Dartmouth Conference, actually took place a year later, but the call for it, the publication of it, was in 1955. And it was a loose gathering of AI experts. So the event took place in 1956. 1956 was also a time when AI entered public popular culture with the release of the film Forbidden Planet, which featured Robbie the robot, an intelligent humanoid robot. And it remains part of popular culture today if we consider, for example, the film Robot and Frank from 2012, which features a robot assistant, intelligent assistant to this gentleman in the picture. and it seems to have been very closely inspired by the Asimo robot from Honda. So turning back to what AI is, I would argue that there's two broad families of AI. A long history around knowledge-based intelligence, based around text and symbols, where you try to capture human expertise in a computer system. And I'll say a bit more about that in a moment. But the current preoccupation seems to be largely around computational intelligence, which is data-based, which includes machine learning for finding patterns in data, largely based on neural networks. You hear the phrase deep learning, which is really just neural networks which have many layers and using large volumes of data. But there are other techniques too, like operational research, which is kind of mathematical form of finding optimal solutions, and genetic algorithms, again, for finding optimal solutions. So I'm going to talk a little bit about both categories. And let's start, though, with the knowledge-based intelligence. And it's been around a while. So if you have a knowledge-based system and not designed to be a sort of personal assistant and advisor, that's generally known as expert systems, and they became very popular, particularly around the 1980s. The first well-known one was Dendril in 1969 for interpreting mass spectrograms. Mycin in 1976 was for interpreting or diagnosing blood diseases. Prospector in 1978 for prospecting for minerals, so geologically based. R1, XCON, XL, all variants of the same thing, which were for configuring computer systems, and that had important commercial implications. SmartGov, and a bit more up to date for configuring public-facing web services. SizeExpert, again, a geological application. And then even more up to date, a system for managing pressure ulcers. Is everything still good in the room? Can you still hear me okay and see the presentation okay? I see lots of people peering at Professor Lee's screen. I'll carry on. So those are all, sorry, I should say, those are all very specialist areas. So they were quite effective, but dealing in narrow domains. And that's a bit of a recurring theme for artificial intelligence. So as I say, it's been around for a while, and I was recruited in the mid-80s to this company called Systems Designers International, and I was actually already working for them when this advert was published in 1985. But as you can see, they were appointing people to AI and knowledge engineering in the 1980s. So what is a knowledge-based system? Well, it has the main distinguishing feature of a knowledge-based system is it has this thing called a knowledge base, which is designed to capture human expertise in a separate area of the system, which is meant to be flexible, adaptable. New information can be added to it, and it's designed to be accessible by domain experts, not computer scientists. The computer scientists or software engineers built the inference engine, which is a program that uses the knowledge that's in the knowledge base and applies it to the current scenario, the current data through the interface. As I've shown, the technology has been around for a while, but it's still being used and still developed. And here's a modern implementation called VisiRule by LPA Limited. And you can see it's got this visual interface. It allows the knowledge engineer to build the information on a screen in this graphical way, and the computer code is automatically generated, as you can see from the window on the right. And it can be applied in all manner of domains. And one I often give as an example is this high pressure commercial boiler, where you could have various rules to control and interpret what's going on. So a simple rule is where you just have if, condition, then conclusion, is known as a production rule. And in this example, we've got a case of if the pressure is above 1 megapascal and the release valve is closed, then you make this deduction about the release valve being stuck. And you can embellish these rules by adding a degree uncertainty. So if those conditions are satisfied, then the conclusion, release valve is stuck, is drawn with a certain probability. And those production rules can be implemented in a language called Flex, and I use Flex for all the examples in my book, and they're all supported on the website. So here's just a few examples. And the key thing is that they're written in very English language style. You don't need to be a computer scientist to understand these. And that's introducing uncertainty and probability is based on Bayesian updating, based on Bayes' law of probabilities, of dependent probabilities. And we've got an example here where we've got some probabilities for these things: temperature high, water level low, pressure high. And you can build these uncertain rules, which now update the probability of the conclusion, pressure becoming high, from its current value of 0.3 based on the input data, by applying the input data based on its probability being true and the weightings attached to the rules. And here's an example I found online, bit of a trivial example, but it shows the sort of thing actually based on CLIPS, which is a publicly available rule-based system for choosing your preference for wine. And you can see that it's made recommendations with different certainties. Moving on to fuzzy logic, which is another form of handling uncertainty. It uses vague language, but has underlying precision. And the key point about fuzzy logic is that the conclusion scales with the degree of satisfaction of the conditions. And an example might be your digital camera on your phone, which adjusts the exposure according to the light level. And it can be achieved with two straightforward fuzzy rules. If the light level is high, then the aperture should be small. If the light level is low, then the aperture should be large. And with just two fuzzy rules, you can achieve a smooth transition to adjust the level of light that enters the camera. So that's a great example of a fuzzy system just based on two simple fuzzy rules. So you can draw a spectrum of intelligent behavior from the specialized areas which these expert systems, knowledge-based systems, were traditionally very good at the top of my intelligence spectrum, these specialized areas which require expertise and planning and adaptability. And at the lower end of the spectrum, we've got a long tradition also of automation based on reaction, regulation, coordination. But it's actually turned out to be the bits in the middle that have proved most challenging to solve. And to illustrate that, consider perception, vision and perception. So here we see a photograph that I took in my garden of three rabbits, in fact, a pet rabbit in the cage, a wild rabbit in the foreground that came to visit, and a rabbit statue in the background. So interpreting things like this have been a difficult challenge for AI. But there have been recent developments using convolutional neural networks, which actually have started now to make a good job of picking out the features in the image. But nevertheless, they lack context. They might be able to recognize the rabbits now, but they lack context. To give you and to explain what I mean, consider this. Here's an image where a system that had been trained to recognize tanks would possibly recognize the presence of a tank here in this image. But it's not a military threat. There's context here, which is really hard to build into an AI system, which just labels things. It doesn't actually understand what they mean. So in this context, we've got a tank, but it has the people on it are not military personnel. It's in a historic setting. It's got marketing slogans on the side of it. So it clearly is not a war scenario, but that kind of context is quite hard to build into an AI system. So I'm going to move on now to machine learning, which is the sort of core heart of the sort of computational intelligence side data-driven side of AI, which is very much driving things forward at the moment. It's basically primarily based on pattern matching. So until very recently, I would have said that neural networks are almost exclusively used for classifying. Essentially, you present a neural network with hundreds, thousands of examples of type A, type B, type C, typically images, and then you present it with something it's not seen before, and it will say, "Ah, yes, I recognize that as being a type A, a type B, or whatever." So classifying. And the other examples here, predicting, clustering, and nonlinear mapping, are more or less the same thing. If you make a prediction using neural networks, you're effectively just classifying it as a scenario with type A, likely outcome, type B, likely outcome, etc. Clustering is grouping similar sets of inputs together. So again, it's similar to classifying them. And a nonlinear mapping is a general linking of sets of inputs to sets of outputs, which are typically a classification, but I suppose they don't have to be. But things have moved on very recently with developments in neural networks for generating new artifacts and large language models in the headlines at the moment, specifically ChatGPT. And I'll talk a little bit about that shortly. And I'm going to cover three broad types of neural networks. The multi-layered perceptron, established as a useful network in 1986, convolutional neural networks, which appeared in late 1998, and then generative adversarial networks, GANs, from 2014. These are three key network architectures, all loosely designed on biological neural networks, which are based on neurons connected by these dendrites. So this is what a multi-layered perceptron looks like. You've got neurons, simple processing units in layers, in this example, 3 layers, from the input layer, then one hidden layer, so-called hidden layer in the middle, and then one output layer. But you can have more hidden layers than just the one. And the idea is that you present repetitively numerous examples as inputs with their associated expected output, and the network will adjust the weights so that it's able to generate the output that you desire from the input that you present, so that when you present it with something it's not seen before, it will produce a suitable output. That's so-called generalization, that it's learned from the examples you present to produce a sensible output. And it became useful really as a practical classifier through the publication of the backpropagation algorithm for adjusting those weights to train the network in 1986. Other algorithms, other networks like the Cahonan network, self-organizing map, are good for clustering. And then you've got things like the simple recurrent network, where you've got feedback from the output to the input. That's really useful for providing for dealing with sequential data, where a particular input is interpreted in the context of what came before. And other variants of that include the long short-term memory. And I'm going to give an example now. And the reason I'm going to give it is because it helps to build up and explain this importance of moving from the multi-layered perceptron to the convolutional neural network. So let's consider classification of handwritten characters. So as I mentioned at the start, the interpretation of handwritten characters was a major challenge for many years, now largely solved. Here we've got some examples of some handwriting and some characters that we'd like a neural network to interpret, to recognize. Now, simply supplying a neural network with the raw bitmap and hoping it will find the appropriate features rarely produces good results. Instead, you need some sort of transformation to pick out the key features. And those key features are called primitives. So in the case of handwriting, the primitives are things like the curves, the loops, and the lines. So here's, just to give a bit of context, here's a set of handwritten characters actually taken from postcodes, you might call them zip codes, on handwritten envelopes. So a really important problem for the postal services to be able to recognize these postcodes automatically. And the way you might do this with a multi-layered perceptron, it would require you to first find the primitives. If you simply presented the bitmap images, the network would not be able to realize that just a slight difference in size, slight shifting to one side, looks very different in the bitmap, and yet it is the same character. You've got to pick out the key features, the primitives. And one technique for doing this is to scan your image horizontally, counting the white to black transitions. So here across the top, initially none, but at the second row where we scan across, we get one transition, white to black. Again, one here, and then further down it becomes two as you pass through a loop in the character A. And you build up this set of counts down the left-hand side, and then you repeat by scanning horizontally, scanning vertically to produce this row of figures here. And then you end up with a set of characteristics, I think in this example it's 24 of them, describing that image. And here's a multi-layered perceptron built using that those sets of primitives, where I've got 24 input neurons, a set of hidden neurons, and then 10 output neurons corresponding to the 10 output digits. If I'm just, in this example, just looking at the digits 0 to 9. And it's a really neat example of how you can build a very effective classifier. But so you could argue that if you want to move on to bigger, more complex problems, all you need is a bigger, massive, multi-layered perceptron. But there are two reasons why that's not feasible. First of all, overtraining. If you just build a bigger and bigger neural multi-layered perceptron, thinking that's going to give you a sophisticated neural network, you will fall into the trap of overtraining. The network will become highly expert at interpreting, classifying its training data, but it will fail to generalize. So in this example of just one input variable x, the example would be that it fits this dotted line, which fits perfectly the input data, but is not generalizing. What you really want is this solid line. Or with two input variables, it would form a close boundary around the examples of class 1 here and here, around the examples of class 3 and class 2, but fails to generalize, would fail to realize, for instance, that an example, a generalized example between these two class 1 regions would also be appropriately classified as class 1, but it's overtrained. The other issue is computational intelligence. It's computational explosion. So, and these two problems are overcome by a convolutional neural network, which is one of the major deep learning algorithms, mostly used for interpreting images, but can be used in other contexts. The key thing is that it effectively finds those primitives automatically. I did a lot of work in presenting my multi-layered perceptron with those handwritten characters by finding the primitives. A convolutional neural network effectively does it for you. So it overcomes two key problems. Computational explosion. If I just built a massive multi-layered perceptron with all those connections, it would rapidly become unfeasible, even with a supercomputer, because it's too computational overload. We solve that with a convolutional neural network by using only selective connections. We also overcome the problem of overtraining that I just described. And it's actually been inspired by the cat's visual cortex in terms of its design. So this is what it looks like. You've specifically an example of interpreting images. You put your inputs straight into the first layer called the receptive field, and then that's mapped onto so-called feature maps, which generate lots of outputs. So these are constantly reduced down again through pooling before being fanned out, and then reduced down again through successive layers, so-called convolutional layers. And what these convolutional layers are doing is picking out the key features in the image. So they're effectively doing what I did when I picked out the primitives. They're identifying features in the image so that the final stage is a classifier very similar to the multi-layered perceptron that I've just shown you. And the connections are very selective to keep it manageable. And to illustrate that, at the very first layer of nodes, you're connecting the receptive field is effectively the bitmap, and you don't connect all pixels in the bitmap to all nodes in the next layer up. Instead, each node, each neuron in the next layer up, the feature map, is connected to a region in the feature map, a region in the receptive field, which is effectively the image. So in this example, one neuron in the feature map is connected to 25 pixels through the receptive field. So it's not fully interconnected. It helps to reduce that computational overload. So it's not fully interconnected. It has these layers of abstraction where you're picking out the features in the image to deliver the classification. And you're constantly reducing the number of outputs from the feature maps through pooling. And it's actually the final stage, the classification stage, that's domain specific. All those stages of picking out features that are quite generic, and that's useful because it means that you can use a trained network, a pre-trained network, and just retrain the last bit, the classification bit. I'm now going to move on to generative AI, which is quite an exciting new development, where for the first time we're seeing examples where rather than just classifying and interpreting based on past examples, we're starting to generate new things, new artifacts like text, design, programs, works of art. And an example that's in the news, as I mentioned earlier, is ChatGPT, an example of a large language model. So I think the advent of this phase started with generative adversarial networks, which have this general structure, where you're trying to generate something new using the generator, which generates a new example, and there's a discriminator which tests how good it is. So to give this a little bit of context, you might imagine that the generator is trying to generate a new work of art, let's say a new Monet Impressionist painting. And you've got the discriminator would be like the curator, the art curator in the gallery, who's trying to recognize what's real and what's a fake. So the generator would generate a work of art. If the discriminator might reject it and say, well, that's not like a real Monet. So that would then feed back to the generator and it would learn to make a better example. On the other hand, if it generated a fake Monet that the discriminator thought was real, that would feed back to the discriminator and it would start to get better and better at discriminating Monets. So as a result of this interaction between the discriminator and the generator, you get better and better works of art, in this case, better and better fake works of art in the style of Monet. And this has really opened up a new avenue for neural networks. So, in summary, neural networks used for pattern matching, typically used for classifying and these other variants of classifying, as I said before. The pre-trained convolutional neural networks can find the generative primitives. Example I gave, an example is AlexNet. That's an example of a pre-trained network, which you can then just train the classification bit of it. I mentioned recurrent neural networks for dealing with sequential data. And deep learning has really launched the second wave of enthusiasm for neural networks 35 years after the first wave, after the multi-layered perceptron became practical. We might contrast knowledge-based systems with neural networks, with knowledge-based systems using explicit human expertise based in quite transparent, clear text and symbols. The neural networks using rich sources of data and deep learning. If we look back at some of the milestones, I already highlighted the Turing article of 1950 in the Dartmouth Conference of 56. I mentioned mycin, that's the system for interpreting blood diseases, and emycin is like an empty version of mycin, which became a shell for building generic systems. Big funding in the 1980s, the initiatives in both Japan, in the UK, and elsewhere that are highlighted in this list. R1, XCon, and XL, I mentioned that earlier, system for configuring computer systems. That was in the news at the time because it was allegedly saving £25 million per annum for the Digital Equipment Corporation, the parent company, which was a lot of money at the time. The publication in 86 of the backpropagation algorithm really launched neural networks as a practical tool. 1997, Deep Blue beat Garry Kasparov, which was a real milestone because, as I said right at the start, chess used to be a big challenge for AI, effectively solved then. Convolutional neural networks in 1998, again, a big breakthrough, as I've already alluded to, and likewise, generative adversarial networks, or GANs. Now, since 2000, I would say the big trend has been that these things have become bigger, better, and faster as we've had better, more powerful computer systems. But equally, I think ChatGPT is a major development now, published in November last year. So why all the hype now after this long history? Well, I would say you've got maturing ideas. A lot of these ideas have developed and been refined. Got lots of data to drive forward machine learning. We've got genuinely new deep learning algorithms. We've got internet resources. So all this information is available on the web of various quality, but it's out there that computer systems, intelligent systems can draw upon. We've got faster computers. And then, of course, I mentioned ChatGPT, which is really exploiting those internet resources as vast quantities of data. And I've got a little example, which I ran actually just yesterday to try it out. So I asked it, what is the history of AI? And it gave me an example which started with the history of AI, can be traced back to ancient times. Then moved on. It's talked about AI being the term being coined in 1956 at the Dartmouth Conference. Then it talked about the 60s, 70s, the 80s, and the 90s, what happened in 2000s, and then current widespread deployment of AI. So, you know, obviously you can see I've edited out all the text just to give you the flavor. I came back to it and said, well, wouldn't you say that the modern history of AI began with Alan Turing? And it responded, so yes, indeed, that's true. And then I said, what about generative neural networks? And he said, yes, indeed, those are very important recent development. And then I finally said, do you think there's still a role for knowledge-based systems in AI? And it said, yes, there's still a role for knowledge-based systems in AI, particularly in areas where it's important to have a clear and explicit representation of knowledge. So it basically backs up my point that these techniques are complementary. And to illustrate that, one of the things that I've been involved with for many years is multi-agent systems where you bring together different techniques working collaboratively as a team. The particular model I'm used to working on is the blackboard model, where you have your multiple agents alike humans gathered around a physical blackboard. But in the computer system, they're software agents that communicate via an area of shared memory called the blackboard. And to give you an example, I mentioned earlier recognizing handwritten characters to interpret postcodes or zip codes. But knowledge-based AI gives you a way of validating and verifying whether those zip codes are true. So in the UK system of postcodes, there are only 7 valid postcode formats where alpha represents, where A represents an alphabetic character, N represents a numeric character, and you've got these 6 valid formats of combinations of alphabetical and numerical characters. The third and fourth are the most common ones, and the bottom one has only one specific example. So you can use that knowledge verify what's coming out of your machine learning algorithm. And there's other knowledge too. The letter J is not used in either of the first two alpha positions. Letters Q, V, and X are not used in the first alpha position, and so on. And I've used this multi-agent approach to AI in a range of different applications illustrated in this montage that includes things like controlling multiple model-sized helicopters working collaboratively, interpreting these industrial ultrasonic images, controlling manufacturing machinery, controlling communications networks, controlling or monitoring the state of nuclear power plant. At the bottom right here, interpreting, recognizing mouth ulcers to spot the cancerous ones. For delivering better logistics for rail freight companies, image registration to overlay different types of medical images here, in this case, thermal and visual, and again, image registration in the middle for quality control for spotting print defects. And then finally, in this montage, automated umpiring, recognizing the pattern of play in table tennis. So back to my spectrum of intelligence, I would argue that AI's history started with great success in the specialist area of the intelligence spectrum, complemented by what we wouldn't necessarily call AI, but certainly automation at the bottom level of the spectrum. But the difficult areas were the areas in the middle, which we're increasingly having success in delivering. So in conclusion, AI has a long history dating back to 1950. I can see we're now bridging the spectrum of intelligence with complementary AI techniques. But my key message would be, don't rely on the data alone. Knowledge gives context and understanding to what's coming out from machine learning. DARPS, the multi-agent system that I've been involved with, is available through my website. I'm trying to build an open source community for it and to develop new real world applications. Finally, the advert for the book, which Professor Lee mentioned earlier. The 4th edition of my book is available now, Intelligent Systems for Engineers and Scientists, a practical guide to AI. If you go to my website, adrianhopgood.com, you will see there's a discount code available there. Thank you very much for your attention. I hope that was that you were able to follow that in the live audience, and certainly at least with the online audience. Thank you very much. You're on mute, Professor Lee.